In the previous video, we developed several different formulas for finding calculus concepts for parametrically defined curves. We found an expression for the derivative, for an integral, for arc length, and for surface area. In this video, we will practice using these various expressions to find derivatives, areas, arc lengths, and surface areas for parametrically defined curves. Let's start by looking at example 1. Here we have the parametric equations x equals sine of t and y equals t times cosine of t. So we could write this first one, we could write it as x of t just to remind us that x is a function of t. And the second one, this is y of t to remind us that y is a function of t. First, what we want to do here is to find the derivative of y with respect to x. So for the x equation, we have x equals sine, and the y equation, y of t is t times cosine of t. Now, using the formula that we developed, the derivative of y with respect to x is the derivative of the y function divided by the derivative of the x function. Now, taking the derivative of the y function requires using the product rule. We have t times cosine of t. So when we take the derivative, we can't just use 1 times negative sine. That's not correctly taking the derivative of a product. So for the numerator, using the product rule on t times cosine of t, we have the derivative of t, which is 1, times cosine, no derivatives, and then we add t times the derivative of cosine, which is negative sine of t. So there's the derivative of the y function. Now we simply divide by the derivative of the x function, which is cosine of t, and we have our expression for the derivative of y with respect to x. This tells us the slope at any point, where we can simply plug in a t value and get the slope of the line at any t value we would like. So this was part A for this problem. Part B asks us to find the point on the curve when t equals pi. So we want to find the point on the curve when t equals pi. When t equals pi, we simply plug pi into the x and y functions. So x of pi is sine of pi, and then y of pi is pi times cosine of pi. Now let's draw the unit circle here. So we get the values for sine of pi and cosine of pi. Pi is this angle here. Sine is the y value, so sine is 0. Sine of pi is 0. Cosine is the x value. Cosine of pi is negative 1. So we have pi times negative 1, or negative pi. So the point on the curve is 0, negative pi. That's the answer for part B. Part C asks us to find the equation of the tangent line when t equals pi. Now we can find a point on the tangent line. That's the point that the curve passes through when t equals pi. We can find the slope of the tangent line by plugging in pi to our expression here for the derivative. So the slope, well, first of all, the point is 0, negative pi. And then the slope is the derivative when t equals pi. So we have this expression. We're going to replace all the t's with pi. So we have cosine of pi plus pi times negative sine of pi, all divided by cosine of pi. And from the unit circle, we know that cosine of pi is negative 1. Sine of pi is 0. So we have negative 1 plus pi times 0 divided by negative 1. Negative 1 divided by negative 1 is positive 1. That is our slope value. So we have a slope. This is what we could call m. We have a point. When we have a point and a slope, we can use the point-slope form for the equation of the line. So we're going to use the formula y minus a y value equals the slope times x minus a specific x value. So the y value of the point is pi, so y minus negative pi equals m times x minus 0. And the m, that's the slope, that's 1. And so we have 1 times x minus 0. So we have y plus pi equals x, or y equals x minus pi. So this tangent line has a slope of 1 and a y-intercept of negative pi. Let's take a look at Desmos to visualize these parametric equations along with this tangent line. So to sketch this parametric curve, we have x equals sine of t, y is t times cosine of t, and we'll go ahead and look at this just from -10 to +10. This is actually a really cool parametric equation. Look at this thing. Doesn't that look cool? It's this weird loop-de-loo stuff. We are going to find the equation, or we did find the equation of the tangent line when t equals pi. So let's see the point where that occurs. So we'll replace these lowercase t's with a capital T. We'll add a slider for capital T. And we want to know when t equals pi. So when t equals pi, we get that point. That's exactly the point that we expected, 0, -pi. And the equation of the tangent line we found to be y equals x minus pi. There it is. There's the equation of the tangent line, just as we expected. Now notice that this would be impossible to do in terms of Cartesian equations. If we wanted the tangent line at this value, well, this is when x equals 0. But notice that we have another point when x equals 0. We have another point when x equals 0. So what is the equation of those tangent lines? Well, that would be ambiguous. So this is not, y here is not a function of x. This would very badly fail the vertical line test. But using parametric equations, we can find a specific point here for this specific value of t equals pi, and we can find the equation of the tangent line at that point using parametric equations. Let's solve example 2. We are going to set up an integral to find the area under the curve, parametrically defined by these equations, on the interval from 0 to pi. Now notice these equations. Hopefully these look familiar from the last section. We have x equals cosine, y equals sine. The parameter t ranges from 0 to pi. This is going to sketch out exactly half of a circle in the upper positive y values, and we will be able to find the area under this circle, that's the area of half of a circle, using parametric equations. So first, let's sketch what these equations look like. Again, we have x equals cosine, y equals sine. These equations together are giving us the unit circle, and we're told that the parameter t ranges from 0 to pi. So this is only going to sketch out half of the circle. Here it is. We're taking this equation, this is from -1 to +1 because it's the unit circle, and we are going to find the area under the curve using parametric equations. Now, I'll just mention here that we could also do this in terms of Cartesian equations. We could write a Cartesian equation for this graph. This is y equals the square root of 1 minus x squared. And we could set up this area using Cartesian equations. We could write the area as the integral from -1 to +1 of the square root 1 minus x squared dx. Now, this integral is not a very nice integral to work with. It's rather complex, and even just looking at it, it's difficult to determine exactly which integration technique to use. So this does give us the area of half the circle, but it's not a very pleasant integral. Let's look at the integral that we get using parametric equations. So the integral for parametric equations is going to be the integral from alpha to beta of the y function times the derivative of the x function, integrating with respect to t. All right, so we have the integral. We're integrating now with respect to t. So these values of alpha and beta are the 0 and pi. So the limits of integration are from 0 to pi. And we have y, that's just sine of t, times the derivative of the x function. The derivative of the x function is negative sine of t, dt. So positive sine times negative sine, we have a negative. So I'll take the negative out front. We're integrating from 0 to pi, sine squared of t dt. Hopefully this integral looks familiar. We can solve this using a trigonometric identity. We can use the trig identity here. Sine squared of t, in this case, equals 1/2 1 minus cosine of 2t. So we can convert this sine squared of t using that trig identity, and we're still integrating from 0 to pi. I'm going to go ahead and take the 1/2 out front of the integral right away. So I have a negative 1/2 out front, and then inside I have 1 minus cosine of 2t. Integrating cosine of 2t, this is one of those integrals where we do a u substitution without writing down all the steps. So we'll write negative 1/2 times the integral of 1, which is t, minus the integral of cosine, which is sine, of 2t, and then we divide by 2 to compensate from the chain rule. We're integrating from 0 to pi. So we first put in the pi, negative 1/2 times pi minus sine of 2 pi divided by 2, minus negative 1/2, so minus a minus is a plus 1/2, times 0 minus sine of 2 times 0 is 0, divided by 2. Now, sine of 2 pi is 0, so this fraction is just 0. Sine of 0 is 0, so that fraction is 0. So the value that we get here is negative pi over 2. So going back up to our picture, we found an area here of negative pi over 2. Now wait a second. This area is above the x-axis, so we would expect it to be positive. Yet using this integral, we got a negative area value. Why is that? Well, here's the reason. The curve, if we integrated from negative 1 to 1 with respect to x, the curve is going this direction. We're adding up area from negative x values to positive x values. When we integrate from 0 to pi, t equals 0 gives us this point. So we're actually, instead of adding up area, we're subtracting area going backwards from t equals 0 to t equals pi. So that's why the area that we got was negative. We could fix that at the start by integrating from pi to 0, and that would be adding up area going in the positive x direction. So we shouldn't let this negative pi over 2 bother us too much. We could say that the area, since it's above the x-axis, is really positive pi over 2. Now, does this make sense geometrically? We have half of a circle with a radius of 1, and what's the area formula for a circle? The area formula for a circle is pi r squared. We're taking half of that. So this is the area formula for a circle. We're taking half of this, and the radius is 1. So we're taking 1/2 times pi times 1 squared, which is just 1/2 pi. Oh yes, that's what we got using these parametric equation integrals. So essentially, we just proved the area formula for a circle, which I think is pretty cool. Take a look at example 3, and notice the similarity between example 3 and example 2. We just found the area under this parametric curve, and we saw that this is half of a circle, so we found the area for a circle, and now we're finding arc length. Well, arc length along a circle is just the circumference. So what we're going to do for problem 3 is to find half the circumference of a circle with radius 1. Let's give it a try. So once again, we'll sketch out our circle, and we have x equals cosine of t, y equals sine of t, and this is being traced out as t ranges from 0 to pi. Now recall when we first talked about arc length. One of the examples that we did was to find the arc length of the curve x equals the square root of 1 minus y squared. That was this curve here. This was half a circle just oriented sideways, and we found the arc length using the Cartesian expression for the arc length integral. Now if you remember, this integral involved arcsine. It was rather an unpleasant integral. We are going to find the same value in terms of parametric equations, and the integral that we get here is going to be much nicer than the integral that we got when we worked with Cartesian equations. So first of all, let's write the arc length integral. Arc length in terms of Cartesian equations is the integral from alpha to beta of the square root of the x function derivative squared plus the y derivative squared, integrating with respect to t. So we have the integral from alpha to beta of the square root, and let's take the derivative of the x function. So the derivative of the x function is negative sine of t. We're squaring that, plus the derivative of the y function. The derivative of y is positive cosine of t. And once again, we're squaring that, integrating with respect to t. The upper and lower limits now are from 0 to pi. Now at first glance, this integral might look rather unpleasant, but we have sine squared and cosine squared underneath the square root. So we could write this negative sine squared is the same as positive sine squared. So this is sine squared of t plus cosine squared of t. And what do you know about sine squared plus cosine squared? This equals 1. So we have the integral of the square root of 1, which is just 1. Look how simple this integral is. No arc signs. This is wonderful. The antiderivative of 1 is just t from 0 to pi. We plug in pi, subtract 0, and we get an answer of pi for the arc length along this curve. Now, this is half of a circle of radius 1. The circumference for a circle is 2 pi r. Here we have a radius 1, so the circumference of the entire circle would be 2 pi. We're taking just half the circle, so half of 2 pi is simply pi. We found the arc length, or half the circumference of a circle, using a very nice integral, which was much nicer than the expression we got when we did Cartesian equations. So this shows us one advantage for working with parametric equations. Sometimes the integrals that we get with parametric equations are much simpler than the integrals for evaluating the same exact expression in terms of Cartesian equations. So this is one nice advantage that sometimes happens with parametric equations.